Good morning, seventh graders. Today we're going to be moving on to 15.3, where we talk about experimental and theoretical probability. Okay, there's a difference between the two, and we're going to talk about that today. Right? So for our key idea, right away, we can get into what experimental probability is. It says experimental probability is probability that is based on repeated trials of an experiment. Right? So this is like, I'll say you flipped a quarter and you wanted to see, or you wanted to experiment how many times you got tails. Okay. So you flip your quarter 50 times and you get tails 24 of those times. Okay. So if you wanted to find your experimental probability, or what you found for when you did your experiment, you would get tails 48% of the time. 24 divided by 50, it's almost half, is 48%. Now, theoretically, so in theory, what would you expect? Well, in theory, since there's only two possibilities, right? You could either get a head or a tail. There'd be two possibilities, and you're trying to get the one possibility of a tail. So in theory, it'd be 50% of the time you would get tails, but when you conducted your experiment and you found your experimental probability, the number of times that you flipped tails versus the total number of trials, you got 48%. So there's a little bit of a difference there. We'll work on those with our examples today. Finding an experimental probability. For example 1, it says the bar graph shows the results of rolling a number cube, so again like a dice, 50 times. What is the experimental probability of rolling an odd number? Okay, so these are our, right, a dice has 6 sides on it, and it wants to know what's the experimental probability, so when we did our experiment, of rolling an odd number. So rolling numbers 1, 3, and 5 are our odd numbers. Okay, so that's the probability of rolling an odd number would be the total number of times the event occurred. So how many odds did we get? Well, we have to do 10 plus 8 plus 11. That would give us 29 over what was the total number of trials? Well, it's set up here. We roll it 50 times. Okay. So all you need to do is 29 divided by 50, and you can just punch it in your calculator if you want. But when you do that, you get 0.58. And again, to make this decimal into a percent, you just move your decimal 2 spots to the right, and that equals 58%. Okay. So when we did our experiment, it was 58% of the time we got an odd number. Now, theoretically, what should that be? Well, there's 3 odd numbers and there's 3 even numbers. So in theory, or theoretical probability, you should get an odd number about 50% of the time. Now, was that close? Pretty close. But when you only roll it 50 times, it's probably not as accurate. Say if you were to roll it 500 times, you'd probably get closer to this theoretical probability. In the second example, now we'll use that experimental probability to make a prediction. So it says it rains 2 out of the last 12 days in March. Okay. If this trend continues, how many rainy days would you expect in April? Okay. So the probability of raining in March was it rained 2 out of the last 12 days. If I were to simplify that, that would be 1 out of every 6 days, right? I just divided by 2 on top and bottom. Okay, so this is my trend. Now, if I want, I could make this into a percent, right? I could take 1 divided by 6 and I could say, okay, it rains 16.67% of the time. But I'm just going to leave it as this for right now. It rains 1 out of every 6 days. It says, if this trend continues 1 out of every 6 days, how many rainy days would you expect in April? Okay, well, to make this prediction, we just need to multiply our probability here of a rainy day by the number of days in April. Let's see, what's the saying? 30 days has September, April, June, and November. So April has 30 days, you can see here by the calendar. So all we need to do is take our probability and multiply it by the number of days in April, which is 30, or same as 30 over 1. Okay, so 1 times 30 is 30, over 6 times 1 is 6, and 30 divided by 6 is 5. So we can expect that there will be 5 rainy days in April. I should probably capitalize April. Okay, and you could do that other ways too. You could say, well, 1 in every 6 days. So 1, 2, 3, 4, 5, 6. It's going to rain on this day and not these days. And you could kind of follow that pattern, and you'd get the same result here. But you just need to multiply your probability by the total number to find how many you'd expect for making that prediction. I'm sure you've heard that old saying, April showers bring May flowers, right? Okay, please pause the video now to try examples on your own 1 and 2. Okay, the first one says, in example 1, what's the experimental probability of rolling an even number? So there was 21 evens out of a total of 50, which would give you 0.42 or 42%. And number 2 says, at a clothing company, an inspector finds 5 defective pairs of jeans in a shipment of 200. So again, if you wanted to, you could make this into a percent. You could simplify it if you wanted to. It doesn't really matter. Remember, this is the same as if I simplified it, divide by 5 is 1, divide by 5 is 40. So this is the same as for every 40 pair of jeans that you get, there's 1 defective pair. It says, about how many pairs of jeans would you expect to be defective in a shipment of 5,000? Okay, so what you could do is, like we just did in that last problem, is you could take your probability and you could multiply that by the total. So here's our probability, and we want to multiply that by our total of 5,000. So 1 times 5,000 is 5,000, divided by 40 times 1 is 40, and 5,000 divided by 40 would give you 125. That's the most common way. You could also set up a proportion. I see a lot of students do this. They say there's 5 defective pair in every 200. Question wants to know how many pairs of jeans would be expected to be defective in a shipment of 5,000. So our totals are on bottom, and our defective are on top. So you could just cross multiply. 200 times x is 200x equals 5,000 times 5 is 25,000. And then just divide each side by 200. And you'd get the same thing, x equals 125. Both work. I'd encourage you to know both ways. They're both pretty helpful. Okay, for the key idea, number 2, it talks about the theoretical. So in theory, now we're not doing an experiment, but it says when all possible outcomes are equally likely, the theoretical probability of an event is the ratio of the number of favorable outcomes to the number of possible outcomes. Okay, so kind of similar to what we've been doing with setting up that ratio. Okay. So it says you randomly choose one of the letters shown. So all of these letters are in a box or in a bag. You pick one out. It says, what's the theoretical probability of choosing a vowel? Okay. Well, the probability of choosing a vowel is the ratio of the number of favorable outcomes. So, in other words, how many vowels are there? Because those would be the favorable outcomes. I see an E, an O, and another E. So, how many favorable outcomes are there? Well, there are 3 favorable outcomes. And then how many number of possible outcomes? Well, how many total letters are there? 1, 2, 3, 4, 5, 6, 7. Okay. So 3 out of 7 is your probability. Or if you wanted to convert that to percent, you could do 3 divided by 7, which would give you about 43%. So the probability of choosing a vowel is about 43%. Right? Example 4 wants us to use theoretical probability. And this is kind of like that second on your own problem, but it says the theoretical probability of winning a bobblehead when spinning a prize wheel is 1 in 6. So 1 out of every 6 times you could win a bobblehead. And it says the wheel has 3 bobblehead sections. So how many sections are on the wheel? Okay. Well, let's set up our ratio here. So the probability of winning a bobblehead is the number of bobblehead sections, because this is that would be the favorable outcome, right? If we landed on because we'd win a bobblehead, divided by the total number of sections. And this is what we're trying to find. We don't know that, right? How many sections are on the wheel? That's what we're trying to find. So let's set up a proportion. We know that the theoretical probability is 1 to 6. That should be equal to this theoretical probability that we just wrote that ratio of over here. How many bobblehead sections are there? What's the number of bobblehead sections? Well, there's 3 bobblehead sections. It wants to know what's the total number of sections. That's what we're trying to find. So we're just setting up that proportion, very similar to the last problem. Okay. So 1 times x is x equals 6 times 3 is 18. And that makes sense because if there were 3 bobblehead sections and a total of 18 different sections, you could win on 3 of those 18. Well, if you simplified this, if you divided top and bottom by 3, you'd get 1/6, which is exactly what we started with. All right, pause here for 3, 4, and 5 on your own. Number 3 says, what's the theoretical probability of choosing an x? Well, there's only 1 x, and there's 7 numbers, so 1 in 7. Or if you divided that, that's about 14.3%. Number 4, the theoretical probability of spinning an odd number on a spinner is 0.6. The spinner has 10 sections. How many sections have odd numbers? Okay. So this spinning an odd number is, right, 0.6 is the same as 60%. So if there's 10 total sections, what is 60% of 10? We're looking for that top number here. How many sections of odd numbers? That would be 6 sections. And then lastly, for number 5, the prize wheel was spun 540 times at a baseball game. About how many bobbleheads would you expect to be won? Okay, so remember it was 1 in 6 is your theoretical probability, and it says it was spun 540 times. Right, and we're trying to find how many you'd expect to win. So again, cross multiply. 6 times x is 6x equals 540 times 1 is 540, and then just divide by 6 on both sides. So you get x is equal to about 90 bobbleheads. Let me know if you had questions on any of those. And we'll wrap up here with the last example, where we're going to compare experimental and theoretical probabilities. So it says the bar graph shows the results of rolling a number cube 300 times. What is the experimental probability of rolling an odd number? Okay, so again, we're working with the odds. So numbers 1, 3, and 5. So we'll have to add our odd numbers that we got. So 48 plus 50 plus 49 would give us a total of, so the probability of rolling an odd number, when we add our 3 odds, should come up with 147 over, remember the total, so we rolled it 300 times. And when I divide that, I get about 49%. Okay. Letter B says, how does the experimental probability compare with the theoretical probability of rolling an odd number? Well, what is the theoretical probability of rolling an odd number? Well, in theory, you have 3 odd numbers over a total of 6 total numbers. So in theory, you should get an odd number of about 50%. The theoretical probability is about half the time, right? So how does that compare with the experimental probability? Well, our experimental probability we found is 49%. So it's very close to our experimental probability. And the more times that you do something, the closer to your expected or theoretical probability you're going to get. Letter C says, compare the experimental probability in part A to the experimental probability in example 1. So if you remember in example 1, our experimental probability was 58% versus our experimental probability here was 49%. So 58% in example 1 compared to 49% in example 5. Okay, so what happened there? Well, we became closer to the theoretical probability. And again, because we rolled it 300 times now, not just 50. So we're getting a more accurate when we do an experiment more times. Okay. Lastly here, pause for the last on your own and try it out. Okay. It says use the bar graph in example 5 here to find the experimental probability of rolling a number greater than 1. So what you need to do is you need to take 53 plus 50 plus 52 plus 49 plus 48. And yes, I'm just plugging this into my calculator, which you can do too. And you come up with 252 times that you rolled a number bigger than 1 over the total number of times, which is 300. So 252 divided by 300 would give you a probability of about 84%. And that's our experimental probability. That's what we actually got. It wants us to know what's the theoretical probability of rolling a number greater than 1. Well, theoretically, how many numbers could you roll that are greater than 1? Well, you could roll a 2, a 3, a 4, a 5, or a 6. So what's the total number of outcomes, of favorable outcomes? 1, 2, 3, 4, 5. 5 favorable outcomes out of a total of 6 on a number cube. And 5 divided by 6 would give you 83.33% of a theoretical probability. So 83% of the time, you're going to roll a number that's bigger than 1. And when we did our experiment, we got 84% of the time. So very close here with our experimental versus our theoretical. Okay, that does it for 15.3 and comparing theoretical versus experimental probabilities. Let me know if you have more questions, and I'll be glad to help. See you guys next time.